Okay, now we're going to discuss about the leakages and also the air movement due to leakage from pressure or due to pressure or due to thermal or due to the stack effect and the phenomena even some air will go in or out due to pressure itself. Okay, from outside. Okay. For the leakage itself, there is a method named air blower or air door blower test or door blower method. It is to identify what is the leakage for a confined zone or a building, etc. It is based on if you have a zone and the zone has a leakage from a certain point at the door, or you're going to run a air with a flow measurement, which is mean you can know what is the flow and what is the delta B between in and out. It is like a U or whatever tube or something with mercury to check what is the delta B, 50 Pascal, 10 Pascal, whatever. Then you will run and you know how much is the flow rate of the fan giving. Based on this, you take some numbers and voila, you can know how much leaking outside. How? See, its expression, it is very simple, which is Q K delta B over N. If we remember before when we discuss here, which is forget there is H static now because the zone is one zone. So head is equal to KQ square. In another way is Q equal K because K is constant. So divided by 2G, whatever. So if it is pressure, so it is divided by 2G, etc. So it is Q equal some constant multiplied by delta B power over half. But actually, it is not always the case, especially in the air, to be power to half. It is a little bit get different than this from the theoretical number. That is why it is always kept as n. And usually n it will be like 1 over 2, but sometimes it will be something else. Okay. Now because it is not like a fittings here and the small here fittings or the charge coefficient like in others, etc. There is a lot of parameters which is absolutely you don't know for a building or for a zone. So if it is a single room, yes, you can know it, like what we do in like here. Yes, which is under the doors. So K already has been get already known. It is under the door multiplied by the area leakage itself. Okay, so it is 0.83 multiplied by area leakage. Yet in our case, we don't know what is the area leakage. We don't know a lot of parameters, so we put it in one big capital K. So the idea is uh, how I'm going to get this. If you start to make the numbers at Q, you get a pressure at Q, you get a pressure at Q, you get a pressure at Q, you get a pressure. Still, you have an unknown of N and K, which is you don't know. Okay, you can do to style and error, of course, to get N and K, but however, there is a logarithmic method which is take the log from the left side and log for the left side. When you take the log, so log Q equal log K plus N log B. And if you start to plot in a logarithmic scale, so log Q as a numbers, log B as a numbers, whatever. So assume this one as an X, assume this one as a Y, assume this one as a constant, or in opposite Y equal C plus N constant. So plot in Y direction and in the X direction. And you know this is log delta B, so you will get one number. Okay, it will be line. So because you get 2, 3, 4 numbers, even if it is a little bit up or down due to accuracy, but you can make a median line. So you know this line, it will continue constant as constant slope. So the slope is constant, and you know that the slope is what? Slope is y divided by x, which is this one divided by this one. We know the slope is like this. So it is n, by the way, which is n. Okay, because we know this is like a, a formula for a linear. So the slope of this line is n, which is a factor multiplied by x. So from the slope you can get n. While you know n, you put it in any result you get. Q at b, you have n, so you can get k. Okay, so k is a constant, will be, and n will be as a constant. So you can apply it anywhere else. So what is the significance of this? For example, in case of Dubai, the maximum infiltration rate, it is 5 meter cube per hour per meter square of the envelope at 50 Pascal. Maybe we'll do the test at higher Pascal or even lower Pascal, but when you get K of that building and N of that building, you can define the is it you're meeting this one or no? And even you can depend on these numbers for later on if in case of you have a higher or super high rise building, but later on we're going to get it. Okay. This is what we discussed for the stair, because we know this one and we know this one. If it is doors, it will be 1 over 2. If it is cracks or windows, it will be 1 over 1.6. Okay. This is only for the stairs applicable, or for rooms which is have doors. Okay. Now we're going to discuss something else, which is thermal air leakage, which is mean there is an air movement from a zone to other due to the difference in the temperature. How? Imagine that you have a building, and the building air inside is high and air outside, temperature of course, is low. So air inside will go to air outside due to delta temperature. Based on this, C is the discharge coefficient, which is can also varies from if it is a window, if it is etc., and if it is a crack or whatever. But usually it is discharge coefficient is almost 0.4. However, it can be validated by doing modeling. Okay, and this application maybe like for if you have a hot smoke and you are opening a window with a natural ventilation to outside, it will use this way to get to have a resultant. And by the way, it is a transient mode, which is mean when the too much smoke is accumulated, which is mean more hot and hot smoke is accumulated, which is temperature inside getting higher and higher. So flow rate will be higher. Why the flow rate get higher? The temperature of the smoke at the top layer get less. So from here, the flow rate get less. So it will be like this fluctuating. There's one already done just to show it. Yeah, this one of our projects, which is done the simulation based on it. And by the way, this is a simulation, which is you can see it start accumulated very hot, then the flow rate was small, then the flow rate start to be bigger, then it is go way up, see way up, then it's become colder, then it is start to reduce down again, the smoke layer, until it is reached to the steady state condition. And how it is happen, flow estimated low based on correlation, smoke layer height. Oh yeah, this is CFD result. So you can see from the result is started like this, then reduced, then start to isolate till it is reached to a certain level. Okay, so the last point is regarding the stack effect. Stack effect, it is not a pressure It is not a thermal, it is a combination between these two, or not a combination, it is due to temperature difference, it is creating a pressure. How is the stack effect? See, stack effect, if you're going to have, it is, if you have a building like this, or a core, whatever, you have a zone, and this zone, you know that is the temperature in this zone, the walls, the stairs, everything is at 24, for example, and you know outside is 46. If you start by anyhow, let that air enter here by any method, so you will have a 46 Celsius air getting in contact with solid areas with 24, so that air will cool down. What will happen when the air cool down? It is go down. So it will create high pressure here and will create less pressure up. And in the opposite case, if you have here 10 Celsius at winter and you have 0 Celsius at winter and you have here 24, so it will be in the opposite case. Okay. So how to calculate or how to deal with this? See, in case if you have a stack effect, normally from the stack effect you will have, because he will be high pressure, he will be low pressure, or in the opposite case, but you will have one line which is going to be equals, okay, because it is low then high. So where is the median line? It will be here. Approximately it is from 1/3 to 1/2 of the total height, approximately. Okay, and we discuss why. So delta pressure is what? Delta pressure, it is Ks, which is it is a factor, by the way. 346, this is an SI unit, 1 over T out in Kelvin over 1 of T in Kelvin multiplied by the distance, which is you want to study, for example, at the full height. So the distance of the full height measured from the natural plane, which is we already discussed about it, the natural plane. Okay, okay. It can be from this one to this one, which is create what is the pressure it will be. Okay, okay. Based on these fundamentals, we can define the super high-rise building infiltration consideration and what we are going to have. So in super high-rise building, we have an infiltration going inside the building, even if we try to eliminate it. Okay, so let's study first the stack effect on the infiltration, not on the pressurization, huh? Not in the static pressurization. Static pressurization much easier because we know how much we are injecting as, or we are going to calculate how much we want to inject is the air, and we know what is the pressure limitations what we have. Don't exceed the 70 pascal or the 80 pascal, even sometimes 85, and don't decrease than the 50 pascal or even 30 pascal in some cases. Okay. Okay. We're talking now about the infiltration going to happen. So the infiltration, we know it is creating a delta pressure based on what is temperature inside, what is temperature outside. Okay, we know what is the temperature inside and what is the temperature outside, but still we don't know how much infiltration we have. But because we know there's a delta T, it will create a pressure differences. Okay, and according to how tight is the building, we can understand how much infiltration it will go. And this action needed to be studied floor by floor, zone by zone. For example, we are in super high-rise building and we are studying the last floor, and we need to check what is the infiltration rate going to be happen, because we know that is the pressure here will go less, and we know that is some air will go like this, because we assume that is by anyhow you don't have super tight building, so you're going to have an infiltration go inside. When you have an infiltration go inside, all the air will jump down, so he will have high pressure, he will have, because here's low pressure, so always air will enter here, always air will escape from here. Okay, so to know about this one, you need to study about this height. So about this height, where it is one, yep, about this height from the natural plane, delta t, you will get delta b. From the delta b, you're going to use the definition, which is the municipality or even other building, which is can be defined if it's super tight, is it steel structure, so it's not tight, if it's not super tight, etc., which is allow up to 5 meter cube per hour per square meter. So check your square meter as an envelope for that floor, then you will get what is the maximum flow. When you have the maximum flow and you have the delta B, and this is the maximum flow by the way, and this is delta B. So based on this, sorry, you will have delta B equal a number, and Q you already can estimate it. Of course, it is just the upper limit. Okay, from that, what you're going to have, you don't know K. This is a point, you don't know K. While you don't know K, of course, but N you know it by the way, because we're going to use the definition of cracks and windows. Okay, so by knowing keeping N as 1 over 1.6, you will get K. When you will get K, forget that assumption, or this assumption can be changed, but you took it as the worst case scenario, by the way. Okay, so you forget that assumption, because this assumption is not valid for all floors, it's not valid for everywhere, but you get K, and you'll use an approximation that is K, it will be constant for each floor. So while you have K, you have delta B for each floor, you have N, we already used it, the approximation is 1.6, you will have Q infiltration difference from each one, from each floor. Of course, when it is above, if in case in hot out, cold in case of above the natural plane, it will be always in, but here is too much, here little, then it will go skip here. So when you are doing your heat load calculation, you need to put an infiltration rate different for each floor, or you can even put it at the maximum for your safe side. So in supervising, we put an infiltration rate, okay? And down, you need to ensure when you're doing a fresh air handling unit is that if you're giving 100 lbs, for example, you know, and you're taking, for example, 90 lbs, you know by anyhow, there is a certain amount going to run outside of the building to make a pressure balance. Okay, okay, for each floor. Okay, okay. Of course, we can assume that is h is equal half of the total h, which is a natural plane. Now we used a lot of approximations. Of course, we use this approximation, but it's very difficult to simulate. But this, it is not difficult to simulate. So in such cases, either we'll use contam, which is a little bit easier for us to get where is the natural plane, and even, or we use the CFD to get where is the natural plane, because we are measuring H always from the natural plane, and you will get the actual flow rates, or you will use the manual ones. Okay, but for professional case, you need not to approximate this one. Of course, if you are going to simulate the entire building, it is impossible. That is, each gap and each hole you can simulate, it is impossible. Okay, okay. Okay, now we know how to run the infiltration due to the stack effect. There is another one, which is the wind. You need to consider if you have a wind, for example, if you have a building and there is wind, of course, we already discussed that this wind is like this, by the way. Okay, that create a delta B over the facade, which is going to make an infiltration. Clear, okay? Which is mean here is high pressure, here is low pressure. So in the face of the wind, it will create. Even in the opposite case, when the wind rotate, it will make swirls behind the building, which is create negative pressure, and this will be high pressure. So even air will go out. But we're going to concentrate about this one to check what is infiltration rate is going, because this effect is very minimal, except if you open the window. It will not minimal. But if it is open, the window is not open, it's okay. But here the pressure is very high, which is you cannot assume even the window is closed. You will have some infiltration air leakage, and it is depending on the height, because we know that is wind velocity. When you go higher, it will be higher, and when the wind velocity is higher, delta V is higher. How to consider it? We're going to use the same concept. This is the infiltration is going inside. It is K multiplied delta V over N. We're going to use N as we agreed 1 over 1.6 as windows or cracks. How to calculate delta B? Delta B, it is a y function of what? Of the velocity. We already agreed before. Huh? You will assume that is the wind velocity will reach to zero. It is an approximation, of course. So when the wind velocity reduced to zero, so the force, how it will be? The force is v squared minus v squared, right? So v minus v, like what we discussed here before. We already studied where is the moving plate? Yep. Which is its definition. It is the mass flow rate rho multiplied by the mass flow rate multiplied by delta V. Delta V is from that velocity to zero, so it is the velocity of the air. So m dot is what? M dot is rho multiplied by the area multiplied by the volumetric flow rate, or it is sorry, it is rho multiplied by the velocity multiplied by the plane, the projected plane, multiplied by velocity again, because from velocity to zero, so it is v squared. Okay. So based on this, we are going to have a function based on v squared, but because v, it is a function of y, as we discussed very earlier, where it is. Yep. Nope. Yeah, like here. So we know that it is, if we use the seventh law, that is the velocity is equal to what is the height over 7 and u infinity at each u, or you can use even the bimunicipality code, or there is other. We're going to open this matter later on in case of study of wind. You can use this approximation, or you can use which is related to the wind. No, it is not saved. However, I'm going to open it later. There is a one approximation for the wind. Yep. It's from the bimunicipality. Yep. So wind is equal this formula, and this formula having c, and so c is the effect of the surface, effect of the height. It is all of it is an approximations. So and c is equal z over z, and etc. You can apply the same one, and z naught, it is the type of, it is in coastal, etc., etc., etc. You will get a velocity in term of y. So this is what we are trying to get. So you will have a velocity in respecting of y, in terms of y. Yeah. So you will have a velocity in terms of y. When you have a velocity in terms of y, you apply that equation. So you have a pressure in terms of y. So you'll have a flow injected inside each floor, and you can add the sum of all of this, which is k. K, you already got it from here, by the way, which is delta B wind minus delta B stack effect over 1 over 1 over n, which is 1 over 1.6. So you can calculate that each one. Okay. Now there is another thing, which is if you have a chimney or a muffler and there is a plume coming out and you need to study is the plume is going to hit that window or whatever. It is depending also a correlation, which is a plume height. Plume height is from outlet, how it will raise up. So this is outlet chimney, how the plume will raise up. The plume height is V naught, which is the speed here, divided by V wind, multiplied by 1 over 1.5, etc., 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 which is B atmosphere. It is a correlation, by the way. T gas minus T ambient over T gas, all in Kelvin, to multiply by the diameter. It is an approximation. To know, of course, you need also to do a CFD. Of course, by here, if you do in the wind, I forgot to say, if you've done a CFD, the approximation or the equations here is for the velocity is meaningless because you can going to do it from the CFD itself. Okay, and also here when you do it, the CFD itself going to get it, but this is an approximation so you can validate your CFD model. Also, there is one point is not related to the fluid, but you need to know it in case if you have any impact. For example, if you have it is solids, by the way. So if you have a force and the force is somebody asks you, okay, if somebody hit a window, is the window going to be cracked? It's not related to fluid, but it's good to understand the philosophy of the force. So any impact, it is changing the kinetic energy till zero. So it is the mass, for example, a car or a person who hit a wall. So it will crash for a certain distance. So the first definition is 2mv divided by t, or it is mass of what will hit multiplied by the velocity squared, his velocity, divided by 2s, and 2s is a crash distance. For example, if you have a window and the window or that glass has a deflection value of a 1 millimeter acceptable, so if you put 1 millimeter here and you know that somebody hit it with 1 meter per second and his weight is like this, you will get the force, which is this is an allowable force to hit that window. Of course, allowable force, maybe it will be wind, so it is the pressure multiplied by the area will have the force. Okay. Of course, if you have a shear or whatever, to check is the glass going to break or whatever, so you'll have the force multiplied by the 50 cross section, and you will get the shear is going to hit, and you have a maximum shear for the material, for the glass, for example. Then you can say, oh, if it is safe, so it is safe. Okay. Now we're going to discuss a new subject.